there's two more concepts that I want to go over. The first is the concept of ratio of parts versus ratio of areas. Okay. So this particular relationship is only true for similar figures. Two figures are similar if one of them can be reduced or enlarged proportionally to be completely superimposed on top of another. Okay? And so for all circles, if I took this circle and this circle, okay, is it possible for me to take this circle and enlarge it proportionally so that it fits exactly over the top of the other circle? Perfectly superimposed? Yes. So all circles, no matter what size they are, they're all proportional to each other. So circles are considered similar figures. We'll talk about in the next few chapters as well what types of triangles and quadrilaterals are similar as well. But part of the reason we start with circles is it's the simplest figure. It is similar, or all circles are similar to each other. If we take a look at these two circles, and let's say this circle has a radius of 5 and this circle has a radius of 3. If we take these two circles here, and I want to identify what is the ratio of their parts. And the way that I'll designate ratio of parts is just the letter P with a little arrow. Okay. If you look at the corresponding parts of these two similar figures, the radius of 5 corresponds to a radius of 3 in the other triangle. So the ratio of parts is 5 to 3. That means any one-dimensional measurement since a part is a measure of one dimension, any one-dimensional measurement will have that same ratio. So what's the ratio of the diameters going to be between these two circles? Diameter is a one-dimensional measurement, so it's 5 to 3. What would be the ratio of their circumference? 5 to 3. And we can test that. The circumference is 2 pi r. So the circumference of this circle, 2 pi r. And if we take the ratio, 2 pi times 5, we don't even need to multiply them out to see why this is going to hold true. The 2 pi, the formula part of this, the generic formula part, will cancel, leaving just the changeable part of the formula, in this case the radius. So our circumference will still have a ratio of 5 to 3. Okay, so any one-dimensional measurement between these two circles is going to have a ratio of 5 to 3. Let's look at what the areas of these circles would be. So if I took the area of this larger circle, which is pi r squared, if the radius is 5, what do I get for my total area here? 25 pi. And my area of the smaller circle, it's still pi r squared, but this time my radius is 3. Gives me 9 pi. So what would be the ratio of their areas? 25 pi to 9 pi, where the pi's cancel. And so the ratio of their areas, which is designated with a A and the arrow, is 25 to 9. Does that fraction reduce at all? No, just leave it at 25 to 9. Okay. This is true for all two-dimensional measurements. Okay, so area is a two-dimensional measurement. We now take length and width into consideration. And what is the relationship between the ratio of parts and the ratio of areas? You can kind of see it right here as well, right? We took the ratio of parts and did what with it? Squared it. So when you're looking at just the generic form of this, if the ratio of parts is m to n, the ratio of areas, which is a two-dimensional measurement, is going to be that ratio taken to the second power. Okay, so ratio of parts is one-dimensional, so it's m to n all to the first power. The ratio of areas is two-dimensional, so it's n squared to n squared. Again, we're not going to get into this until the last chapter of the geometry portion, but what do you think the ratio of volumes will be? If volume is a three-dimensional measurement, we take the ratio of the corresponding parts and do what to it? Cube it. And that is the actual pattern that will be seen in Chapter 8 when we go through this. Okay, but all you need to do for right now is work to understand the ratio of areas is the square of the ratio of parts. Okay, so let's see how this might be applied. Right, if I tell you that you have two circles, one with a radius of 2 and one with a radius of 9, what is the ratio of their parts? 9 to 2. What is the ratio of their areas going to be? 9 squared to 2 squared, so 81 to 4. So it allows you to find what those ratios would be pretty quickly. And where this will come into play and save you time is something like this. Okay, what's the area of a circle that's 8 times the size of the given circle? Okay, if you're given a problem like this, you could try to figure out what the actual dimensions are. With a circle, even though it's two-dimensional, the dimensions are the same because you're dealing with just the radius. But when you look at this, if you plugged in and tried to find what the new circle looks like and solve it, you could come up with your answer. But you could also kind of use this same reasoning. What's the ratio of parts going to be? The new circle is how many times the original? 8. So it's a ratio of 1 to 8. Therefore, what do we expect the ratio of areas to be? 1 to 8 squared, or 64. Okay, and so what is the area of this original circle? Pi r squared, or 100 pi. So what's the area of the new circle going to be? 64 times that, or 6,400 pi. Okay, so if you are able to work through the ratio of parts and how it relates to ratio of areas, you might be able to simplify some types of problems. And this is going to be more apparent, and it'll save you more time as we add different measurements. So it'll help with triangles, it'll really help with quadrilaterals, and so on, as you get different dimensions on it. Okay, but I just want to introduce this. It's going to come up in a lot more detail in the next couple chapters. I just want you to get a sense of what it means.